So the topic is rational function. This is a jump to 3.7. And we defined a rational function as a ratio of two polynomials. Let's say P of x divided by Q of x. So P of x will be an n-degree polynomial. So we'll write it as a sub n x to the power of n plus a sub n minus 1 x to the power of n minus 1 plus dot 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 plus a sub 0. And then the denominator is another polynomial. Let's make the coefficient of this polynomial b and the degree m. So we have b sub m x to the power of m plus b sub m minus 1 x to the power of m minus 1 plus dot 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 b sub 0. So we have p of x is an nth degree polynomial, and q of x is an mth degree polynomial. Now we'll address this how n and m relate to each other, the degree of the polynomials, a little bit later, or perhaps after the spring break, when we'll talk about the asymptotic behavior or the long-term behavior of the rational function. So keep that in mind, that the relationship between the degree of the numerator and the degree of the denominator play an important role. But for the time being, I want to introduce the idea of asymptote of a rational function in general. So I'm going to start with the most basic rational function, y equals 1 over x. So asymptotes. Okay. So for example, as I said, I'll take y equals 1 over x. Now, believe it or not, this is a rational function. 1 is a polynomial, degree 0. X is a polynomial, degree of 1, right? X to the power of 1 and x to the power of 0. So what I'll do now, I'm going to make a little table, x versus y, and on the left side, I'll do positive values. On the right side, I'll evaluate negative values of x. Okay? Now, one thing I know right off the bat, that x cannot equal 0. Eye on me. I know that the laptop is some very exciting information, but so we'll start with 1. Okay, when x equals 1, y equals 1. And let's go larger numbers. So let's go to 10. Well, when x equals 10, you have 1 over 10, or 0.1. Let's go 100. Well, you have 1 over 100. This is 0.01. And you can continue, and here you can reach one conclusion. And the conclusion will be like this: y goes to 0 as x goes to positive infinity. Now, why am I saying that? Because it's clearly evident that if x is a larger and larger number, then y becomes a smaller and smaller number. But remember that y is going to stay positive. So for a reason that will be clear in a few seconds, I'll put the 0 plus. In other words, I approach the value of 0, but from the positive side. Notice that 1, 0.1, 0.01, and then 0.001, and so on. So we keep going down, but we stay positive. On the other hand, what happens if I'll choose a smaller value of x? So 0.1 is a small value. If I'll divide 1 by 0.1, I get 10. If I'll go even closer to 0, stay with the positive side. 1 divided by 0.01 becomes 100. And you can see clearly that we have another property, that y will approach positive infinity as x approaches 0 from the positive side. All right, now let's deal with negative numbers of x. Let's start with -1. Well, 1 divided by -1 is -1. Let's go to -10. Well, 1 divided by -10 is -0.01. And if you go to -100, 1 divided by -100 is -0.0. I missed one. I did it also in the morning, by the way. I'm impatient and I want to go to the next line. So we have the third property here. The third property states the following, that y approaches 0 but from the negative side. Okay? Because notice that if we increase the negative values, go -1,000, -1,000,000, we're going to still have a negative number, but smaller and smaller, closer to 0. So this indication, 0 plus or 0 minus, tells you from which direction you approach the 0. And this happens when x approaches -infinity. And finally, let's use small values of x, for instance, -0.1. And well, this will give you -10. And then we'll go -0.01. Well, this will give you -100. Okay, so the conclusion is this: y approaches -infinity as x approaches 0 from the negative side. Okay, now let me introduce you to limit notations. So now we are talking about notations that are used in calculus. How we express the same thing using limit notation. For example, the first observation that we have, y as it approaches 0 from the positive side as x approaches -infinity. We're going to say that the limit as x approaches infinity, we can drop the positive, the limit of f of x is 0, and we don't need to put the positive side in this case. We're just going to say that. Again, this is what's written is, or the interpretation of what we see here is, as x approaches infinity, f of x approaches 0. That's the interpretation. But we use limit notation. With the limit notation, we don't put error here, we just put the equal sign. Even though x is never equal to infinity, well, infinity is an abstract idea, it's not a real number. Okay, so we put the approaches as arrow, but the value is going to be 0. The second property right there, be written, these times it's the limit as x approaches 0 from the positive side, so the limit of f of x in this case will be infinity. Again, even though infinity is not a number, we're going to keep the equal sign here, we're going to use the arrow under the LIM to indicate x approaches a certain value. Okay? The notation for number 3, all the future engineers, you're going to do this a lot in Calc 1 next semester. Ray, wake up. The limit as x approaches -infinity, so the limit of f of x is 0. And we're going to stay with the 0 here. You can, let's put or here, okay? Either notation is correct. This gives you a little bit more information. And the last one, the limit as x approaches 0 from the negative side. This is important because we are talking about what's something we call one-sided limit. But I'm not going to elaborate on this terminology because this is something we'll elaborate in calculus in Calc 1. But we're going to write it as x approaches 0 from the negative side. The limit of f of x is negative infinity. Okay? So those are the limit notation. Now, let's apply these 4 properties as written here or here to the graph of 1 over x and see how they play out. Again, the graph of 1 over x is something that you've seen before, I hope, but the analysis is good in general. So take this example and extrapolate it later on to other examples. So how we approach this? Let's mark these 4 properties on the graph. So let's see if you can grasp the idea. Gosh, cannot say grasp. So here's our Cartesian. Remember the Cartesian coordinate system, x and y. And let's check, and I'll do it in red. Okay, how we interpret the statement number 1. Okay, and we say let's use the limit notation here. X goes to infinity, y goes to 0 from the positive side. That's what it means. So this would be number 1. Again, as x is large, y close to 0 from the positive side. Statement number 2, x goes to 0 from the positive side, y goes to positive infinity. There you have it. We are on the positive side, close to 0, so this will be statement number 2. And likewise, statement number 3, x goes to negative infinity, y goes to 0 from the negative side. So this is the statement. X goes to negative infinity, y goes to 0 from the negative side. So this is how we interpret statement number 3. And statement number 4, y is close to 0 from the negative side, and x goes to negative infinity. So this is statement number 4. All right. Now, in order to sketch the graph, we're going to look at the value of y when x equals 1 and the value of y when x equals negative 1. So we know that the graph is going to go through 1, 1 and negative 1, negative 1. And now we are really ready to complete the sketch of the graph. Okay, we connect what we call asymptotic behavior to the point where we know that the graph or the curve has to go through, and this is it. Okay, what we'll do next, not necessarily today, we're going to build on this one and we move. For instance, if this graph was the graph of 1 over x plus 2, well, x cannot equals negative 2, so the whole graph will be shifted 2 units to the left, but you know how to do translation. So the rest will be translation of the same idea. Now, if we look specifically at this graph, we're going to say the following, that this graph has a vertical asymptote in this case, the vertical asymptote is the y-axis, so x equals 0. But the vertical asymptote, using limit notation, I can say that the limit of f of x goes to infinity as x goes to 0 positive, and the limit of f of x goes to negative infinity as x goes to 0 from the negative side. Those are the vertical asymptote. It's the same line, but it's two one-sided asymptote as we go from the right and we go from the left. Likewise, we can talk about horizontal asymptote. In this case, the horizontal asymptote will be the line, the x-axis, or y equals 0. And in this case, we're going to say that this will be the limit as x goes to positive infinity, and f of x Actually, instead of error, you want to put the equal sign. Sorry about that. And the equal sign will be 0 plus, and the limit as x goes to negative infinity, f of x equals 0 minus. So these are the horizontal asymptote. Okay. In general, the vertical asymptote will be x equal a constant, and in general the horizontal asymptote will be y equal a constant. So in general, we're going to write the following. This is one particular case where the x and y axis are the asymptote, but the more general case for the vertical asymptote, we have the following. For a generic function, so of f of x in general, we're going to have the limit as x approaches a, okay, f of x, the limit of f of x equal to infinity, or as x approaches a, f of x equals negative infinity. This will be the general form of a vertical asymptote. The general form of a horizontal asymptote, and with that I'll finish. Add to this, the outcome is x equal a constant. In this case, x equal a. Okay? And the next one, the general form will be the limit as x approaches infinity, we have b, or the limit as x approaches negative infinity, f of x equals b. Okay? These two are the general form of the horizontal asymptote, or in general it will be y equal a constant. And you can see in this case y equals a b. All right? With that, I'll finish the discussion. We'll pick up